is why we can build this massive scale infrastructure. And if we look at the inside of the network, we have it basically consists of like the edge. So the edge is basically the network interface card, right? Every server has a network interface card, including the storage server. So that's how every server is connected to other servers. And the network fabric is basically a set of switches, networking switches, right? So the NIC will connect to the switch, and the switches are interconnected, right? So this is the high level concept of a data center network. And as I mentioned, the network is why we can build this massive scale infrastructure. We can simply add more computer servers, and every server has a NIC, right? And we can add more storage servers into the network. So the scaling is just very simple. Okay, so on top of this infrastructure, how can we process data at large scale, right? So on computer servers, we run these database kernels like Postgres, right? And which can execute both SQL queries and transactions, right? And on storage servers, we run some storage specialized systems like RockCB, which is a very popular key value store. It manages SSD devices and provide a KV interface. And normally we process queries at large scale. Then we need more than just one server, right? And more than one rack. So we have to run the computer engine across different computer servers to process data at a large scale. And when the compute engine executes queries or transactions, so the data has to be moved from the storage to computer side, and this is what we call a data movement, right, over the network. And during distributed query processing, we also need to move data across computer servers. And this data movement is the performance bottleneck in large-scale data processing in data centers. It's simply very expensive. All right, so here's I just give a very basic setup for data processing in data centers. So let's look at a few recent hardware trends in data centers that will drive the design of data systems. So the first aspect is compute efficiency, right? So this figure is pretty famous. It shows the CPU performance in recent years. So the x-axis here is every year, and the y-axis basically shows the CPU performance, best CPU performance in that year. As we can see, from 1986 to 2002, we have this perfect Moore's law scaling, right? So we don't need to worry about hardware performance, right? We just build our software and expect that in 1.5 years, the CPU performance will double, right? Yeah, so that's improving the system performance is super easy. However, Moore's law is slowing down, right, as you can see. It's because of the physical limit, right? It's not the CPU performance is not get any significantly faster, and it's very challenging. It's very costly to improve a CPU performance nowadays. To demonstrate this aspect, we run a micro benchmark, which is the compression task, right? Data compression. So you have some uncompressed data. You run the deflate algorithm and compress it into a smaller data. So compression is a very common computer task in data systems. We want to use compression to reduce the storage overhead, right? So we have the original uncompressed data is probably 1 terabyte. If we compress, we only need 500 gigabytes. And we can also use compression to improve the I/O performance, right? We can just reduce the network traffic. So here, so this figure shows the result, right? So the x-axis shows different data size, and y-axis shows the latency, the time it takes to compress the corresponding data size. So if we do the translation, right? So we on a state-of-the-art CPU, which is the AMD EPYC ROM. So this CPU is the one of the most advanced CPUs in servers. With a single core, we can get 500 megabit per second compression throughput. So this throughput is very low compared to the I/O devices like SSDs and network speed. I'll show this I/O device speed shortly. We also run this task on energy efficient CPU ARM. ARM is also very popular. There's a lot of development of ARM CPUs in data centers. Previously, it's primarily for mobile devices like for phones. But nowadays, people are increasingly deploying ARM CPUs in data centers as well. The performance of this ARM CPU is much lower than the AMD one, right? So the compression throughput is only 240 megabit per second. Okay, so hardware channel here is that the CPU, the general purpose compute resources, which is CPU, the performance is not keeping up with the I/O speed. So let's look at the I/O speed, right? So this figure shows the SSD device performance in recent years. And we can see that the most advanced SSD now can provide more than 10 gigabytes per second. So if you do the translation, it's like 80 gigabytes, right? 10 gigabytes is 80 gigabit per second, so which is much higher than the CPU compression speed. We also run a micro benchmark, right? So what we do is that in Linux, right? We randomly access 8 KB page in a NVMe SSD. So this figure basically shows how many CPU cores they are required to achieve certain storage access performance. So here the x-axis shows the throughput, right? How many. So here, like 300 means 300,000 pages per second, and the y-axis shows the CPU consumption. So basically, the general finding is that if you want to achieve more than 500,000 pages per second, you need more than 3 CPU cores. And in the cloud environment, even a single CPU core is kind of expensive. It costs thousands of US dollars in the lifespan of a server. So the second trend is that the storage speed is increasing, and it incurs a lot of CPU costs. I mentioned the disaggregation, right? Which basically means the compute and the storage are separate, right? They are managed in different servers, and they are connected via network. So if we compare disaggregation to traditional server setup, where the storage and the compute they are in one machine, right, which we call monolithic machine, where one server has all the computer resources that are required to perform computational tasks. So now with disaggregation, compute and storage they are connected via the network. Which means that every time you need to access a storage, you have to do network communication, right? So we do another benchmark, which is to transfer this 8 KB, right? Once we read the 8 KB page from storage devices, we have to send them to the computer side, right, over the network. So we run this micro benchmark. We send the 8 KB page across the network using the Linux socket, TCP/IP socket. Again, so here the x-axis shows the throughput, right, the page transfer throughput, and the y-axis shows the number of CPU cores that are required to achieve that throughput. If we want to achieve like some decent throughput, like more than 1,000 pages per second, we need also quite a few CPU cores to dedicated just for that data transfers. So the final trend is that hardware resource disaggregation is happening in cloud data centers. Storage disaggregation is almost the architecture for every public cloud, like Microsoft, Google, Amazon, etc. And the disaggregation kind of amplifies I/O cost. So the conclusion of this hardware trends is that improving the performance and reducing the cost for cloud data processing is becoming increasingly challenging. We have been working on this problem. This is one of the fundamental problems in database system community. We have a proposal which is to use DPU to improve the performance and reduce the cost for cloud data processing. So DPU is basically a new hardware that's gonna replace the traditional network interface card, where we can program the NIC and offload some application logic into the hardware. And so I'll talk more about the DPU shortly. But our result is that with DPU, right, by carefully offloading some of the components to DPU from the server, we can improve different aspects of cloud data processing. All right, just to give a motivation about our DPU work, for the rest of the talk, I'm going to introduce DPUs, which stands for data processing units. And then I talk about two of our recent publications in using DPUs for data processing. So one is the general DPU proposal, and the DDS, which is the specific work under this umbrella. But so far, are there any questions? Cool. All right, so DPUs. So DPUs are essentially the SoC-based smart NIC. So SoC stands for systems on a chip, right? So you have one chip. It's not just a CPU, right? It has many other hardware components that can serve as a machine, right? As a dedicated machine. So DPUs are basically SoC-based smart NICs. A very popular DPU is NVIDIA BlueField 2. NVIDIA is is most valuable company now because of their GPUs, but they also make DPUs. And BlueField 2 is one of the most popular DPUs on the market now. So I will use NVIDIA BlueField 2 as an example to explain the hardware architecture of DPUs. So first, every DPU has a very high-speed network interface. So on BlueField 2, we have a connector X6, which provides 100 gigabit network speed. DPU also has a multi-core energy-efficient CPU. On BlueField 2, there's 8 ARM A72 cores. And a DPU also has onboard memory. So this memory is quite constrained, normally ranging from 8 GB to 32 GB. So on BlueField 2, we have 16 GB. And a DPU also has hardware accelerators that are the hardware that has specialized for certain data path tasks, such as compression, encryption, and regular expression matching. And the DPU also has a PCIe switch, which allows it to access the host resources like host memory, right? Directly access host memory with DMA without involving the host CPU. It can also access other PCIe devices like SSDs or GPUs, etc. So this is basically the hardware components, the list of the components in a DPU. So this figure shows the NVIDIA BlueField 2 DPU board, right? And if we break it down, it basically has the components I just mentioned, right? So it has a connector X6 NIC. It has some hardware accelerators. It has some ARM cores. It has a PCIe switch, and it also has some onboard memory. Okay. And DPU is very popular now. It's not just NVIDIA. Almost every hardware vendor is offering DPUs, including AMD, NVIDIA, and Intel, and some other DPU startups. And cloud providers like Microsoft, AWS, and also Alibaba, they are also making their own DPUs. And they are actually deployed, right? So this is a slide from NVIDIA. It's one of their most recent GPU cluster design. They use the most recent DPU in NVIDIA, which is called BlueField 3, as a NIC, right, to optimize the data movement across GPU servers. Okay, so what are the opportunities for data processing, right, from DPUs? So the first is that the DPUs can be very fast in some computer tasks. For compression, so now we compare the AMD and ARM CPUs with the compression hardware accelerator on BlueField 2. And as we can see, the time is much shorter now. And the throughput, the compression throughput is like 2 orders of magnitude higher than CPU. We further do this decompression benchmark across different hardware platforms, including BlueField 2, BlueField 3, and also one of the most advanced servers. So this figure basically shows the decompression throughput across different platforms. BlueField 3 can provide almost 100 gigabit decompression throughput. This is very high. It basically means that we can do decompression at line rate. So the second opportunity is I/O optimizations. So a DPU, as I mentioned, has a very high-speed network interface, right? It provides hundreds of gigabit per second network interface. And a DPU also has very efficient user space libraries that you can use to build high-performance I/O applications, including RDMA, DBDK, and SPDK. And even better, DPU is closer to these storage devices, right? Because a DPU is also itself is a PCIe device, right? So we have a server which provides some PCIe slots. We plug a DPU into one of the PCIe slots, and the other PCIe slots have other PCIe devices like SSDs, right? So the DPU is a peer to these other PCIe devices. So we can directly access these PCIe devices from DPU, so without going through the host. And the third opportunity is that compared to other smart NICs, right? There are different types of smart NICs. So there are ASIC-based smart NICs, FPGA-based smart NICs, and now DPUs. Compared to previous generations of smart NICs, a DPU provides a general programming because of the onboard CPU cost. So it has a CPU, and with this CPU, you can write any program, right, to compose these hardware resources on the DPU for your customized application logic. So that's why a DPU can support the offloading from different types of applications. Okay, I just talked about these good things about DPUs, but it turns out that using DPUs for data processing is actually pretty challenging for data processing. And the first challenge is the abstraction mismatch. So it basically means that these hardware provided SDKs, software development kits, they target low-level packet processing. Right? So DPUs, essentially they are the smart NICs, right? They are designed for packet processing, not for database systems. So the SDKs provided by vendors, they are not for data processing. So here I list a few SDKs from the major DPU vendors. NVIDIA has a Docker SDK, Intel has People, AMD has SSDK. So if you look at these SDKs, so they're primarily for packet processing, right? You have to specify how to pass the packet headers and specify the match action rules. So basically, you need to program packets, not not the database object. So this is the network packets are too low level for database system developers. So the second challenge is resource diversity. A DPU is a SoC, right? It has a range of hardware resources. Right? It has a CPU, it has a specialized ASICs, yeah, as I mentioned, right, it has quite a few. It has a network interface card, it has hardware accelerators, SoC cores, etc. So given a specific application, so if you want to offload an operation from the application, so you need to figure out how to decompose this operation into the into different hardware resources, right? How to decompose it into tasks that can be executed by different DPU resources. Another challenge is the DPU heterogeneity. I talked about the general DPU architecture, which consists of these 5 resource components. But if you look at the specific DPUs, actually the detailed hardware configurations are quite different. For example, NVIDIA BlueField 2, it has a A72 CPU. It has some compression, decompression, regular expression hardware accelerators. So in the next generation, which is BlueField 3, the CPU is upgraded to A78. And for some reason, they removed the compression accelerator. There are only decompression and regular expression accelerators. And we also look at another DPU from Marvell. Marvell is a DPU startup. They have this Octane TX2 DPU. So the hardware accelerators are quite different from NVIDIA DPUs. So basically, the detailed hardware configurations are very different. I mean, if you use compression, right? For example, if you use compression accelerator to to accelerate your database system to compress the page, then you can't. Maybe your program, right, can work for BlueField 2 and BlueField 2, but it won't work for BlueField 3 and Octane because they just don't have the accelerators. All right. To summarize, so we have a few quite exciting opportunities for using DPUs to accelerate data processing applications, and we also have challenges, right? So this is basically a motivation for our DPU proposal. We want to address the challenge and utilize harvest the opportunities to make cloud data processing execute more efficiently. All right. Any questions about DPUs? Okay, I'm gonna move on to our DPU proposal. Okay. So DPU is basically a platform that is gonna facilitate the data processing on DPUs. We have a few goals. The first goal is we want to bridge the semantic gap between DPUs and data systems, right? Because the hardware vendor provided SDKs and not for data systems. We want to make we want to provide a high-level interface, and we want to utilize a variety of DPU resources for suitable data processing operations, and we want portability. I want to provide this offload once and run anywhere portability. So DPU consists of a few components, right? We have 3 core engines. The first is a computer engine, which is going to orchestrate the computer tasks on DPUs. So this computer engine will utilize DPU memory, the DPU cores, and also the hardware accelerators. And it also coordinates with hosted CPUs and other PCIe accelerators like FPGAs and GPUs, right, to collectively execute some computer tasks. So the network engine will be about offloading the network communication, which is an essential component in data system, in distributed database systems. The network engine will use DPU memory and PCIe devices to coordinate with the host CPU, and it's gonna, of course, it's gonna use the high-speed network interface card to actually transfer the data. And finally, we have a storage engine that's gonna that targets storage efficiency. It's gonna use the DPU memory and also the PCIe access directly to SSDs. Okay, so these are the three components in DPU, and I'm going to talk about each of the components in detail. So the computer engine, right? So we have three specific goals for the computer engine. Right? We want ease of programming because this vendor provided SDKs they're too low level for packet processing. We want this computer engine to be easy to program. We want the portability. We want, of course, we want the efficiency. So stored procedures in recent years have been shown to be pretty effective offload API. So we're gonna use the stored procedure as an interface for computer engine. But the stored procedures, they are designed for CPUs. They are not for the hardware accelerators. And that's why we propose a set of specialized functions, which we call DB kernels. And these kernels are specifically for using the hardware accelerators. So here's the illustration, right? So the application, right, can write their own logic, right, using the CPU, the onboard CPU on DPU. And from there, they can invoke the DB kernels that's going to use the hardware accelerators. And the DB kernels are designed to be portable. So these kernels, these are software abstraction. They can be ported right across different DPU hardware. And if you use the DB kernels to offload, then when you switch to a different DPU, you don't need to worry about like reprogramming your application. So a few challenges. So the first challenge is how. So there will be different sizes of kernel requests. Right? Some kernels they want to process a lot of data. Some kernels they only process a small amount of data. For example, for transactions. How can we schedule these requests in different sizes? And different data processing tasks, they have different performance targets, right? Some they want low latency, some want high throughput. We need to accommodate the different performance targets, and we want the DB kernels to collaborate with the other PCIe accelerators like GPUs to execute some computer tasks at a larger scale. Right. So this is the computer engine. We just again, right? DPU is a proposal. I'm going to talk about one specific solution for the storage engine, but the other engines we know the challenge. We are still developing the solution. Okay. So for the network engine, the key ideas are the network communication is pretty CPU intensive. So we want to offload these compute intensive network communications to our DPUs. So the high level idea here is that we want to provide a lightweight interface on the host server for the application to do the network communication. But the underlying the execution will be done on the DPU, and we want to support the popular network protocols that are used in data systems. And specifically, there are the two most popular network protocols: TCP and RDMA. The TCP, is a very traditional transport protocol. It's reliable, and it remains the most popular protocol in data systems. So the idea here is that we want to provide a socket API. Socket is basically the interface. POSIX socket is the interface for for using for program the networks in Linux. And we want to offload the TCP/IP stack to the DPU, which is the most CPU intensive part. So the first challenge we need to address is as the DPU cores are energy efficient, they are not as performant as the host CPUs. So if we run TCP/IP stack on the DPU, we will experience some performance degradation. So how can we make TCP efficient on the weaker DPU cores? And now the front end and back end are separate, right? For socket applications, and they run on different hardware components. How do we coordinate these two components to to send out the data flows? We need some flow control algorithms. So the second most popular network protocol is RDMA. RDMA stands for Remote Direct Memory Access. It's a user space, right? Unlike TCP, it's not in the operating system. It's directly in the user space, and it's getting more and more adoption in industry. I spent some time at Microsoft. We built some RDMA systems for their cloud native database system. So our idea for offloading RDMA in DPU is basically an extension of Carbird, which we published at SIGCOMM, which is top conference in computer networking a few years ago. So in Carbird, our insight was that although RDMA is more CPU efficient than TCP, it remains pretty expensive. If we can offload this RDMA protocol to the network, which we did with network switch in Carbird, then we can use the saved CPU cycles to run application logic, right, to improve the application performance. So in DPU, our idea is that so on the host, right, on the host machine, the application will not execute the RDMA protocol. They just every time they want to do RDMA, right, they just post their request on local memory data structure. And on the DPU, we have a network engine, right? That network engine will pull from this data structure with DMA, and if there are requests, we're gonna just execute this request RDMA operations on the DPU to access the remote machine memory. So as you can see, the RDMA protocol will be executed by the DPU, not on the host, and the host will only do local memory operations, which are super efficient. And Carbird was for disaggregated memory, which means that it only supports RDMA read and write. So we want to support a full set of RDMA operations, including read, write, and send, receive. Right. So the final component is the storage engine, right? And I'm going to talk about the storage engine as in detail for the last part of the talk. So the idea is basically, the 5 I/O operation on the storage servers are expensive and inefficient nowadays, and we want to leverage the shorter path from the DPU to the storage devices to make to bypass the host for most of the requests and to save some CPU cycles and improve the storage latency. Okay, so we also allow the interactions between different engines in DPU because they are all on the same DPU board, right? They share the DPU memory, so the applications can selectively enable and disable these engines for their own needs. And on top of DPU, we want to support a range of cloud data systems, including key value stores and database systems. All right. To summarize, the reason why GPUs are so popular now is because GPU makes it very easy for general applications to utilize GPUs. In a similar spirit, we want to make DPUs easy to program, right, for data systems. And we offer 3 engines: computer engine, network engine, and storage engine, to utilize various DPU resources for different operations. And the storage engine, which we call DDS, has been developed, which I'm going to talk about later. The other 2 engines, we're still working on them. So, any questions about DPU? Right. Let me move on to the last part, which is about our storage engine. Right. So I'm gonna first give a context about the storage disaggregation, and then present the problems and how we can solve them with the DPU. So as I mentioned, storage disaggregation is happening, right? And I'm gonna just present this architecture with a specific instance, which is Microsoft Azure SQL Hyperscale for short. Hyperscale is a cloud-native version of Microsoft SQL Server, which is a very popular, well-known database system. So in Hyperscale, there are 2 layers: the computer layer and the storage layer. So the computer layer consists of computer servers. Right? There's only one primary computer server that can perform both the reads and writes. Right? So if you look at the database transactions, right? So there are 2 types of transactions: read-write transactions, which can update the database, and read-only transactions that only read from database. They don't update. So the primary node can execute both the reads and writes, and the secondary computer servers, they only execute read-only transactions. And every computer server has local SSDs that serve as a cache. Right? So if a transaction requires some database page, right, some records, this page will be loaded from storage and cached in the local SSD. In the storage layer, we have storage servers, which are called the page servers in Microsoft. Collectively, these page servers store the entire database, and every page server stores only a partition of the database, specifically 128 gigabytes. So let's look at the reads, how reads are executed under this architecture. So we only issue these read requests when there are cache misses, right? So when we execute a transaction or when execute a query, we have a cache miss, right? So the data is not locally cached. Then the computer server will send a request called getPageAddressor to the corresponding page server, which has a page. So this request consists of 2 fields, right? The page ID, right? Which page I'm going to access, and also the LSN. LSN stands for log sequence number, which is basically a version of the page. Right? I want a page, I want this specific version, right? And this request will be sent to the page server that has a page. So the page server, once the page server receives the getPageAddressor request, it's gonna look up its local pages, right, and see, do I have the version that satisfies the required version? If yes, I'm just return that page, right, back to the computer server. If not, I'm just gonna wait, right? Wait for the page to be updated. And how pages are updated are through the write operations. And in Hyperscale, they perform writes with additional service called log service. So every time the primary node executes this write transaction, right? So this transaction will generate some log records. So these log records will be sent to this log service. And from where these log records are further distributed to the secondary computer nodes and also page servers, where these log records are replayed to refresh the local page. So that that's why the secondary computer servers and page servers can refresh, can update their keep updating their local pages through log replay. As we can see, these write operations, they are much more complicated than read operations, right? Okay, so there are a few benefits of storage disaggregation. Better scalability and elasticity, because you can scale compute and storage independently, right? They are not in one server. If you want more compute, you just get more computer servers. If you want more storage, you get more storage servers, right? So it's more elastic. And also it's more available because the storage layer can be dedicated to the cloud storage service, which can provide some availability guarantees, and thus the eventual benefit is lower cost, because you just use whatever you need, right? You don't need to over provision resources for your workloads. And storage disaggregation is a defining feature of cloud systems. So here I listed a few examples. So database systems from AWS, which is Aurora, Alibaba, we have a PolarDB, Azure Hyperscale, Google has AlloyDB. They are all built on top of this storage disaggregation architecture. And this architecture is not just about database systems. Other data systems like key value store, they also adopt this architecture. Okay, so the primary challenge of storage disaggregation, which is a result of this CPU slowdown, is basically the CPU consumption and the latency. So we did a benchmark. So we measure the CPU consumption on the page servers in Hyperscale. I did this benchmark when I was at Microsoft. I spent a gap year there after my PhD graduation. I did this benchmark, and so this figure basically shows where the CPU cycles are spent, right, when process these get page addressing requests on a page server. So as we can see, most of the CPU consumption happens within the database system, right? It's an internal communication stack. And the networking stack in the OS and the storage stack in the OS, they only contribute a small part of the CPU cost. So this basically means that the kernel bypass, kernel bypass is technology that removes the operating system from the critical path. So it can improve the I/O efficiency. But our results show that with kernel bypass, you only get rid of this OS overhead, but the majority of the overhead happens within the database system, right? And because of this software overhead, the latency of this get page addressing is also very high. Okay, so we can use DPUs to address this challenge. So the DPU, the advantage of DPU is that it sits on the fastest path to service disaggregated storage requests. So I'm going to demonstrate this by comparing a DPU architecture with a traditional disaggregated storage architecture. So this is a traditional disaggregated storage server where we have a NIC, a network interface card. We have the host memory and a host CPU and some storage devices. Right? So when a request arrives on the NIC, so the NIC will do DMA, right, to send this request to the host memory, which will be processed by the host processor, right? And the processor will read the page from SSD, and the SSD device will do DMA to send the page to the host memory, and finally the NIC will do DMA to read the page from a host memory and send it back to the client, to the computer server. As we can see, there there's a round trip over the host, and this will incur a lot of software overhead. So with DPU, we can do better. Like once the request arrives on the DPU, we can directly access the SSD without involving the host. And once the data is read from SSD, we send it back to the client, to the computer server. So this is how we can bypass the host with DPU. So that's just one advantage, right? I also talk about the I/O optimizations and the general programming advantages for offloading. So we can leverage these benefits to offload the different storage requests. Right. So these are all the benefits, right? All the advantages. So DPU has some quite significant disadvantages, significant limitations for offloading storage requests. So the first is WinP CPU cost, right? They are not as performant as hosted CPUs. So we run this workload. This is a production workload from Microsoft. It's kind of faster. Faster is the production key value store. And we run the read modified write on both the hosted CPU and also the DPU cost. And here, so the blue line shows the throughput that we achieve on the host server, right, with different number of threads. And the red line shows the throughput we can achieve on DPU cost. And we can see that with 8 CPU cores, we can achieve more than 2 times higher throughput on hosted CPUs than the DPU. So the second limitation is a memory constraint, right? As I mentioned, the DPU only has moderate memory. On Bluefield 2, we have only 16 GB memory, which is an order of magnitude lower than what's required in executing updates. For example, in the log replay in database system, and also the read modified writing in the key value store that I just mentioned. So they read a lot more memory than what a DPU can offer. So this basically indicates that the DPUs are not suitable for offloading writes. They're good for offloading reads, but not writes. Okay. So that's why we propose DDS, right? We want to use DPUs to best optimize disaggregated storage. So like a traditional disaggregated server, we have a host, right, where we run the disaggregated storage applications, like database system, key value store, which use OS operating system to do I/O. We also have a SSD device, but the new thing here is a DPU, right? So now we have a DPU to replace the traditional NIC, and on the DPU we run DDS. And our core idea is a partial offloading. So we only offload the operations that are suitable for offloading on the DPU. And for the operations that are not suitable for DPU offloading will be forwarded to the host, right? To be executed by traditional, like existing disaggregated storage stack. Okay, a few design questions we need to answer, right? So the first is how do we access the SSD files directly on the DPU? And the second question is how can we separate the traffic between the host and the DPU? And finally, how can we make the offloading on the DPU general and fast? Okay, so let's look at the first question, right? So the problem with accessing SSD files on the DPU is that the file mapping is actually managed on the host, right? So we on the host, the application, the storage applications, they use a file system in the operating system to create the file and then access the files. And the operating system, right, specifically the file system component, that maintains the file mapping, which maps the file to the physical disk blocks on the SSD. So on the DPU, right, we don't have, right, given a request, right, they specify the file ID, right, which file to access, and which part of the file it accesses, and the size of the access. So on the DPU, we just don't know how to access, right? We don't know the mapping, right? I mean, even if we can access a file mapping on the host, every time we update some file on the host, we have to manually synchronize these changes to the DPU. So yeah, it's basically pretty costly. And our solution in DDS is a unified file framework. We basically let the DPU process all the file requests. To do this, we provide a library on the host, which offers the same file API as the existing file system. So the applications don't need to change, right? They access files as they did previously. So this library will basically accept these requests, right? So this request will be then forwarded to the DPU, where we have a file service that will execute these requests, right? This is how we maintain the file mapping on the DPU. So now with the disaggregated storage request, we can offload it to the DPU because we have the file mapping. And we did some other efforts to make sure that this file service is efficient. Okay, I'm just talk about the second question and skip the final one, given the time constraint. So the problem with separating traffic is that this partial offloading, which means that we offload some requests to the DPU, some requests will be executed on the host. It will break the end-to-end transport semantics. So in a traditional disaggregated server architecture, right, so the client will establish end-to-end connection, TCP connection with the server, and then the requests and responses are communicated, right, with this end-to-end connection. With the partial offloading, the problem is that it will mess up this connection. I'm gonna give a very specific example, right? Let's say the first packet, right, first request is not suitable for DPU offloading. Okay, we forward it to the host, right? That's all right. So the second question is, it's good for offloading. Then we just offload, which is also okay. But now the problem is that if we have another request that is not suitable for DPU offloading, we send it to the host. The host will not recognize this request because it's expecting the second packet, right, second request, not the third request. So then the TCP will think, okay, the second request is dropped in the network. So it will ask the client to resend this second request. So this basically messes up this end-to-end semantics. So our solution is TCP splitting. We basically have a component on the DPU called a traffic director, which is essentially a TCP IP stack. So instead of having one connection, we have two connections. So we have one connection from the client to the DPU, where we accept all the requests, right? And for every request, we're gonna decide whether we should offload it to the DPU or forward it to the host. And if we forward it to the host, then we're gonna use the second connection, right, from the DPU to the host. Although the idea seems simple, it's very challenging to run a TCP IP stack on the DPU. So we did a lot of optimization to make sure that this traffic director will not become the performance bottleneck. All right, I'm gonna skip the last one. Yeah, our paper, which was published at the VLDB last year, it's a top conference in databases, has more details about our system, how we exchange message between the host and the DPU, and how we maintain the state on the DPU to support general offloading, and also how we build this user space I/O, including the TCP IP stack, and also the file service. Please refer to our paper if you're interested. I'm going to quickly show some results, right? So we set up a test bed for storage disaggregation. Right? We have a client, right? No. So we have two servers, right? Both run Windows Server. We use a Windows Server rather than Linux because I was at Microsoft. And these two servers, right? The client is connected to the server with a 100 gigabit network link, and on the storage server we have a DPU, NVIDIA BlueField 2 DPU, and DDS use. So we divided DDS with almost 15 lines of C++ code. It's a lot of development. And on the DPU, we use 3 out of 8 ARM cores, and we use under 1 gigabyte GPU memory. We supported 3 applications. The first is the remote file application, where this client will just randomly access a big file on the storage server. We also run faster, which is the key value store, and also Microsoft Hyperscale on this cluster. So we first measured, how many CPUs can be saved by DDS, right? So what we do is that in the file application, we randomly access 1 KB page on the storage server, right? And we measure the achieved storage end-to-end throughput and the CPU consumption, right, on the storage host. So here, this figure shows the result, right? So this shows the achieved throughput. So with DDS, we can achieve more than 700,000 pages per second. With the server, right, traditional server, it only achieves like less than 50%, about 50% throughput. And what's exciting here is that with DDS, we utilize a 0 host CPU, while the baseline will consume more than 10 CPU cores on host. So basically, DDS can save host CPUs. We also measure latency, right? So this figure shows so the x-axis shows the achieved throughput, and the y-axis shows the latency, right? When achieving that throughput, this is a tail latency. So this red line shows the baseline, and this blue line shows the DDS. And basically, we can achieve much higher throughput with much lower latency than the baseline. So DDS can lower latency as well. So these results basically generalize to other applications as well. All right, to summarize, this disaggregation is a popular architecture in data systems, but it incurs a lot of CPU overhead, and the latency is kind of high. And if we can use DPUs, DPUs has many opportunities to optimize the storage disaggregation. And in DDS, right, we propose this partial offloading to utilize DPUs for the most suitable operation. All right. So we open source the DDS, and this is a GitHub link to the repo at Microsoft. We also have we also ported DDS to Linux. My students are still working on this. So this is a team that is working on this DPU direction for cloud data processing. Right? The project is basically led by my 2 graduate students, Qizhen and Felix, and with some 2 IA and also undergraduate students at the University of Toronto. We also have collaborators at Microsoft Research and National University of Singapore. Okay, I'm just gonna stop here. Thank you. Any questions? Yes, we do. I mean, I'm working on computer systems research, right? When we evaluate our approach, we have to the best case is to set up a real test bed, right, and actually deploy that system on the physical test bed. For this research, we purchased some DPUs from NVIDIA and AMD. We have our own servers. We are using the cluster to evaluate our approach. For DDS, as I mentioned, we had two servers, right? Here. So this was a setup at Microsoft Research. I also purchased a Bluefield, NVIDIA Bluefield 2, which is installed on one of the servers, and we actually have the physical hardware, and we deploy our solution on the hardware and then actually run production workloads to measure our system behavior. Yes, last year. Yeah. Yes, we do. As I mentioned, I work on system research, which requires a lot of evaluation, and a big part of my startup grant is for